In this video, we discuss about search in AI. Search is one of the important components in training an agent in AI. And as we have discussed in the first video, if the agent has to be trained or if the agent has to achieve certain goals, it may not be obvious to it in the beginning how to act to achieve that goal. So in that case, it may have to do search. The search problem can be addressed in the following way. Agent has certain word. Word at any time may be in certain state. And in that state, if the agent is in that state, it may be able to take certain actions in that state. And a result of that action is that it may reach in another state of the world. And to take that action, there may be some certain costs associated. So what the agent has to do is, in solving the problem, to reach from the initial state to some goal state. And to reach there, the purpose of the agent is to find a sequence of actions that it has to take such that it will reach the goal, and it wants to do it in the least cost possible way. So this is the problem that we are addressing, how for an agent to be in one state, to go to another state, the goal state, what actions it should take so that it can accomplish that, it can reach that goal with minimal cost. We can represent this problem by a graph. In the graph, the state, different possible states of the word of the agent can be represented by nodes A, B, C, D, E, and so on in this graph. If it is in some state, let's say C, then the possible actions it can take is the arrows denoted by the edges with these directed arrows which are coming out of this. So the agent in state C, the only possible action it can take is this action, and it has a cost 3 associated with it. And once it takes that action, it reaches state F. When it is in state F, then it can take two possible actions. One will take it to E, the other will take it to H, and the cost associated in this act is 2, and in this act is 1, and so on. So we consider that initially the agent is in state A and it wants to reach state G or H. So in this case, we are considering there are two possible end states. If it reaches in either one of them, it has achieved its goal. There can be one goal state or more goal states. For generality, we will consider here that the initial state called the root state or root edge in this node in this case, and the goal states are G and H. In the initial simplest scenario, which called uninformed state search, in this case, the agent at any given time has minimal information. All it knows is the state it is in, the vertex in the graph, and the possible actions it can take. So this, if it is in state this, all it knows is that it is in this state, and the possible actions it can take is that these two possible, this and this actions it can take in the associated costs. And once it takes these actions, it will reach in these states. So this is all it knows at any given time. This is called the search to find the solution by the agent in uninformed search. There is a general framework for that to obtain multiple algorithms. This is called best first search. In this case, you start at the root node, and the next node you will choose is, or next action you will choose is, among the possible actions available to it, is to go to one of the adjacent nodes where it can go, but we need to choose the node with minimal function fn. If the node is n, there is a function associated with it, fn, function value. So at any state, if you are in state E, and the possible actions you can take is this and this, and which action it will take is depending on which of these states have less function value fn. This has fg as function value associated with this. This has fh. This will evaluate fg and fh, and it will go to the node which has minimal fn value among the possible states or nodes it can go to. Now, what is this fn? Depending on the different possible fn we choose, we will get different algorithms for search. And what are the criteria for the performance? Of course, that way we can obtain many different search algorithms, and we want to evaluate their performance. One is completeness criteria. An algorithm is complete if it finds a solution if one exists. Cost. The algorithm should find the optimal, least cost solution. And an algorithm that we may be discussing may or may not find that. Time complexity. If the algorithm is able to find a solution, then we want to know what was the time associated in finding the solution. The time could be number of edges or steps or actions that it has taken to finally arrive at the goal. Space complexity. There is certain memory requirements associated with each search process, and obviously if the space requirement is less for an algorithm, that will be the desired algorithm. The first algorithm that we obtain this way is what is called breadth first search. In this case, if the function fn, we choose is the depth of the node n. And what is the depth of node n is, we are at root node A. For any node in this, let's say this node, its depth will be defined as the minimum number of steps or actions you have to take to reach from A to E. For example, to reach E, you have to go take one action and then another action. So 2 actions. There's another possibility. You could have taken this, this, and this. So this way it will be 3 actions, but we define the depth equal to the minimum number of actions needed to go from the root node to that particular node. So fn for each node is going to be the depth of that node from A. And in this algorithm, if you are at any state, then the next step that you have to take is, among the possible steps, choose the node which has the least depth. Okay. So this is how this algorithm is defined. You start at the root node, visit all nodes at depth 1, then visit all nodes at depth 2, and so on. So in this case, you are at A. There are 2 nodes at depth 1. So you will come to, those nodes are B and C. You can come to B, and then you can come to C as well. So all nodes at depth 1 you will visit. After finishing that, then all nodes at depth 2 you are going to use. So in this way, starting at A, you can go to B. You could have gone to C as well. So from A, first you will go to BC. These are the nodes at depth 1. Then DEF, these are the nodes at depth 2. You will go there. Then after that, you will go to nodes at depth 3. So those are these 2 nodes. And both of these nodes are goal nodes. So via this algorithm, you go from A to BC. Then from that, you go to depth 2 nodes, D, E, and F. And then you go to next depth, that is 3 depth node, that is G. And as soon as you reach G, you stop the algorithm. So this is called breadth first search. This algorithm is complete because it guarantees if there is a solution, if there is a goal state or node, this algorithm is going to provide you, and you are, of course, able to reach from root node to the goal node. There is a path, then it guarantees you will obtain a path. And the goal node, there are multiple nodes like we have here G and H. The one that you will get via this algorithm is the shallowest goal node. Shallow means the goal node which has the least depth from the root node. Drawbacks of this: the time and memory requirements are high in this case, because in this case what you will do is first you will visit all nodes at depth 1. Then you have to go to all nodes at depth 2. But which are the nodes at depth 2 that you have to do calculations and then visit one at a time to those nodes. To do these computations requires high time and memory requirements. If each node has B children and the goal is at depth D, then time and space complexity of this algorithm are O B raised to power D. Next algorithm is Dijkstra's algorithm or uniform cost search algorithm. This is a popular algorithm available in graph theory. And this algorithm is obtained if Fn for each node, the function at node n, should have a value equal to the path cost from the root to node n. And what is the path cost to node n? You are at root node A, and path cost to any node, for example, node B, is the least cost path from A to B. In this case, the least cost, of course, is this path, which has a cost of 1. The path cost to C is 3. Path cost to E from A, so there is one possible path via this way. So this has 1 plus 1. Total path cost is 2. You could have also come via this way. Here the path cost will be 3 plus 3 plus 2, 8. So these are the only two paths to go from A to E, and we have to pick the least cost. So this path. So from A to E, the path cost of E is 2. So in this algorithm, you start from root node and then go first to the node which has least cost path from A. So in this case, obviously B has the least cost, which is equal to 1. So from A, you go to B. Now, after going to B, which node you should go? The possibilities, and in this case, we don't have to just choose nodes which can be reached from B. You have to just pick the node which has the least cost path from A itself. So after going to B, you have to choose which node you should be going. You could go to C, that has a cost of 3, minimum cost. You could go to D, it has a cost, minimum cost or path cost from A is 3, and to this E, the minimum cost is 2. So this is the node which minimum path cost from A after B. So from A, you go to B, then from that, you go to E. And after that, you can go to D because this was the least cost path. After that, the next least cost path from A to any other node is this. So then you go to A, B, D. This is path cost 3. This is also path cost 2. So you also go to from A to C. This is how you cover going to different nodes at any given time. You keep going it till you get the goal, G or H, right? So this is the Dijkstra's algorithm. Comparison of breadth-first and Dijkstra's, or which is also called uniform depth, uniform cost algorithm, is that in breadth-first, you are at any time covering the same depth nodes. First one depth node, then two depth node, and so on. In case of Dijkstra algorithm, you are covering the same You are covering the same path cost from the root nodes at a time. And then you go to the next higher and so on. If C star is the cost of optimal solution, epsilon is the minimum step cost in the graph, then worst case time space complexity of Dijkstra algorithm is of the order of b raised to power 1 plus, this is the floor function, C star by epsilon. You take the floor of that is the largest integer less than equal to C star by epsilon. So the time and space complexity, the worst case, it can be less, but worst case complexity is O raised to power O order B raised to power 1 plus this quantity. It can be greater than order of B raised to power D, which was the complexity of the breadth-first. If the all costs on the in the graph are equal, then this complexity reduces to of the order of b raised to power d plus 1, which is roughly the same as this breadth-first. Dijkstra algorithm is complete if there is a path from the root node to the goal node in the graph, then it is going to get you the a path, and that path is going to be the optimal cost path. So this is the advantage of this algorithm compared to the breadth-first, because in breadth-first you may not get the optimal path. Depth-first, this is another algorithm by taking fn to be another quantity, and in this case you take fn equal to minus depth of node n from the root. And depth we already defined. Depth is the number of steps or actions, minimum number of steps and actions that you have to take from A to that particular node. So this quantity depth is different from the least cost path. It is just the number of steps, minimum number of steps that you have to take. On least cost, the total path length should be minimum from the root to the goal node. So in this case, you are at A, the depth of B and C is equal to 1. So you will pick, these are the only two possibilities. You take minus of that, minus 1 in both the cases. And you have to take the least Fn. So each one of the Fn's are same. Let's say we take B. So from A to B, in first step, you go to B. After that, once you are here, you want to choose the node with the maximum depth possible from this point. So you can go to D, E, and C, right? So depth of C is 1, depth of E is 2, and depth of D is also 2. So you have to pick from B either D or E. So let's say next step we have taken is we reach to D. Once you reach D, now there are possibilities of E and G where you can go from here, and we pick the node with the maximum depth, right? Because minus of that will be the minimum quantity. And in this case, that is G. So via this algorithm, we went from A to B to D to G. There are, of course, other paths. Instead of going to B in the beginning, you could have taken C and gone further. So, but this is one of the solutions. The cost of this path, because now we have reached the goal, is 1 plus 2 plus 5, which is equal to 8. This is not optimal solution because a path from A to B to E to G, which we will get through the Dijkstra algorithm, that has a cost of 5. Depth first is not cost optimal. The solution that we have obtained is, as we have seen in this example itself, is not cost optimal. It provides the first solution it obtains. For finite graphs that are trees, and trees are the graphs which have no cycles, directed cycles, because we have a directed graph, this algorithm is efficient and complete. Complete means that it provides you a solution if one exists, And efficient is efficient in terms of memory and time. For example, it requires much less memory than some of the previous algorithms. Therefore, it can be a method of choice in many AI algorithms because it is efficient, although it may not provide the optimal solution. Limitations of depth first. For so here we talk about finite graphs when there are number of nodes finite. For cyclic state spaces, for graphs there which can have cycles, it can get stuck in an infinite loop. You can keep going back and back through a single loop again and again. So that, of course, will not time and space complexity can really become bad. For infinite state spaces, where are in the graph infinite number of nodes, it can get stuck going down an infinite path because at any node you are going along a node which has maximum depth, and it is possible that you can just follow an infinite path, so it will keep going it on the path. There may not be a goal node, so you will never achieve a goal, and you will never stop even when there are no cycles in this case. So therefore, infinite graphs for infinite graphs, DFS algorithm is not complete. There is a variant of DFS, backtracking search. It requires even less memory because here it requires less memory, at least for finite graphs with no cycles. But you can get even better algorithm, a modification of this called backtracking search that can provide less memory. We are not going to discuss that here. Now, for depth first, we have just seen that there can be issues if the graph has cycles and or if the graph could have infinite number of elements. So there are improvements provided to take care of that. One is called depth limited search. In this case, you do choose node with higher depth, but you can put a maximum limit on the depth, beyond which you are not going to do the search. For example, I keep the maximum limit of depth to be equal to 2. So I'm not going to look at any node which have a depth more than 2. So, but it is still depth first. From A, you will go to nodes which have 1 depth. This is the maximum depth, and because these are the only possible nodes B and C. So you can only go to nodes of depth 1. You go to A, B. Now at B, we are going to choose, if we chose to go from A to B, we are going to choose the node which highest depth. And that, so you are not going to choose C now, you could go to D and E. So these have depth of 2. There is no other node you can go at higher depth. So therefore you choose one of them. Let's say we chose D. Once we have reached this depth, then what you can do is you can choose to go to E because that also has same depth. You will do that, but you will not go to G. And also, once you reach E, you will not go to G because G is at depth 3. Similarly, even H is at depth 3. Therefore, after that, you get stuck. You will not reach the goal. So the issue in depth limited search cases, if you limit your depth too low, like in this case, we limited depth to 2, we did not get the solution. So poor choice of L can fail to provide solution, and therefore, in that case, the algorithm is not complete. How to take care of this problem? That the depth limit L that you choose should not be too low. For example, if you take the limit L to be diameter D of the graph, and what is the diameter of the graph? This is the maximum distance in number of hops between any two nodes in the graph. If you limit your depth L to the diameter, then there is no issue. I mean, you will get the solution. For example, in our previous example, that the only example we are considering this video again and again, is the diameter of the graph is 3. You pick any 3 nodes, you will be able to use any 2 nodes, you will be able to go from one to the other within 3 steps. So if you take D and H, from D you can go in 2 steps. From A to G, you can go in 3 steps. From B to H, you can go in 2 steps, and so on. The maximum number of steps needed from between any 2 nodes, that's called the diameter. And in this case, in this graph, it is equal to 3. So if depth first, depth limited, we took the limit equal to 3, then we would have obtained the solution. However, in general, in practice, the graph may be very large, and then it may be very difficult to find the depth D of the graph, and then you may not be able to do this. The time complexity of this algorithm is of the order of b raised to power L. B is the number of branches from each node, and L is the limit that we choose. Space complexity is of the order of b into L. Now, next we consider iterative deep algorithm. In this case, like depth limited case, we took the limit L. In this case, what you do is you iteratively increase the depth limit. So you start with the limit of 1. If you get the solution via that, then you do take, if you get the solution via that, you stop. If you don't get the solution via that, then you take the depth limit to be 2, and depth first you can do with that limit. Even then, if you didn't get the solution, then you take 3, and so on. It combines the benefits of depth first and breadth first, because in the previous slide, as we saw, if we don't know the diameter, then taking L a priori fixed may not guarantee that you will get the solution. And of course, you don't want to unnecessarily increase the depth. So therefore, this is a compromise solution. It has the benefits of depth first and breadth first. Like depth first, its memory requirements are low. They are of the order of BD. D is the diameter, if the solution exists. It's of the order of BM on finite graphs when no solution exists. And M is the maximum depth from the root node that we are starting. And like breadth first, the optimal for the problem with the same cost. So this algorithm optimal if all the links have the same cost, and it is complete on finite acyclic, when the graph doesn't have cycles, state spaces. Time complexity is of the order of b raised to power d when the solution has depth d, or of the order of b raised to power m when there is no solution. Now, there are obvious issues with this algorithm because you are starting the algorithm with the L is equal to 1. Then if the solution is not found, then you go to L is equal to 2. Then you go to L is equal to 3. So when you are at L is equal to 1, you have visited all nodes with depth 1. When you are at L is equal to 2, you first visit all nodes with depth is equal to 1, and then all nodes at depth equal to 2. So in this case, once you reached L is equal to 2, you have visited the nodes at depth 1 twice. So this way, as L increases, the nodes at depth 1 will be visited L times again and again. So this is a waste of time. But so why we are considering this algorithm? In the worst case, in the asymptotic time, as the number of nodes increases, it is same as best first search algorithm. In general, iterative deepening is preferred uninformed search method, one of the preferred. When the state space is larger than the memory, so you are not able to keep all these states in the memory, or when the solution depth is not known. So what you are doing is you start L is equal to 1, 2, and 3, and as soon you don't know at what depth your solution or the goal node is. So as soon as you get the goal, you stop. Example, same example. So for iterative deepening, you start with L is equal to 1. So you visit all nodes at depth 1. The nodes at depth 1 are B and C. You stop L is equal to 1 here. You have not found the solution. Now you increase L is equal to 2. So you go to nodes, again visiting at depth 1. Then nodes visiting at depth 2. So these are the nodes as we have seen earlier. And you won't go beyond that and you have not found the solution. So you go to L is equal to 3. Now going to L equal to 3, you will get the solution. A, B, D, G. And you stop there. And incidentally, in this case, as we saw earlier, 3 is also the diameter of the graph. So far, we have been doing this search starting from root node and finding a path towards the goal node. But we can do bidirectional search. In this, forward direction is starting from root node and start searching the goal node. At the same time, simultaneously, you start from the goal node and start going backward. So in this, forward means you go along a path given by the direction in the edges. When you go backward, you are going to go along an edge, but in the direction opposite of the arrow given in the graph, because you actually are starting from the goal. Your aim, of course, is to come to the goal. Okay, so this is what you do. You simultaneously start search from in the forward direction as well as in the backward direction. At each step, pick the node. So you are at one stage and you have to now visit the next node. So you could either do in the forward direction or in the backward direction. Among the two possibilities also, you pick the one with the minimum Fn. So this is our basic algorithm. Next node to visit is the value with the minimum value of Fn. And this Fn now could be in forward or backward direction. Now, what function f's to choose? Earlier, we have seen three different possibilities that we considered, and that those gave different algorithms. What you can do here is you can choose Fn for the forward direction. Let's say one of these three possibilities of f, and in the backward direction you can pick another one, right? So forward direction could be depth first, and the backward direction could be breadth first, if you chose appropriately the functions Fn. But at any given time, whatever Fn you have chosen for the forward and backward, the next node to visit will be picked from anywhere on the forward or backward cases with the minimum Fn at that time. Example. So we are going to give this example for the cost from the root in the forward direction and cost. So basically in the forward direction, the cost of that node from the root. In the backward direction, cost from the goal, right? Now, in this case, we will say we will restrict ourselves where the goal is only one, that is G. So now you start in the forward direction, let's say, you consider A, and you have chosen the costs from A to those nodes. So the possibility in the forward direction B or C. The cost from A to B is 1. Cost from A to C is 3. So among the two possibilities, you will pick this. But you will still not move to this because we have to look from the backward direction also. Backward direction, the possibilities are starting from the goal node. You have to go in the direction uh, like here you are going to from the node to this in this direction. Here you have to go in the opposite direction. From G, it is possible to go to B, E, or F because this is reverse. Now, in this case, you look at all these three possibilities. The cost is from G, 5, 3, and 5. So the minimal cost node is E. In the forward direction, you are choosing the possibility A to B with cost 1. In the backward direction, we are choosing the possibility from G to E, which has a cost of 3. Among 1 and 3, this is lower. So we are going to take the first step to go in the forward direction from A to B. So you go from A to B. Now, once you are at B, again, you are going to, in the forward direction, take different possibilities. This, and this 3 are possibilities. And among the 3 possibilities, you pick the cost, choose, calculate the cost of each one of them from A and pick the node which least cost. So D has cost 3, E has cost 2, and F has cost 6. So we are going to pick D. So this is in the, we are going to pick E. So in the forward direction. While so we reach E, and then of course, because from G the cost was again minimum cost was 3, and therefore we are picking this column A, B, and E. You reach here. Now again, going forward, we have to take the next step because we have not reached the goal. From goal, you can reach this in 3. From this, in the backward direction, from this you can reach the goal again in step cost of 3. So we can pick either from here to here or from here to here. So we have basically met here. So what is the solution we got is A to B, B to E, E to G, right? We got the solution. Performance of bidirectional search. If forward and backward paths meet, as in this case they met at node E, the time complexity of this is of the order of B raised by D plus 2 plus B raised by D by 2, where D again was the diameter or maximum depth. And so you can say this is of the order of B raised by D by 2. This is much less than of the order of P raised by D that we have seen with the other algorithm. It requires tracking in both directions, forward direction as well as backward direction. Forward direction we have been doing all through, but the backward direction, now we have to, look possibilities in the opposite of the arrow from the goal node and going backward. If Fn is cost from root or goal and C star Fn, which is, we are taking this possibility that we took in this example, and C star is the cost of optimal solution, then the state of the cost greater than C star by 2 will not be visited by the algorithm. So this can speed up the search substantially. So this can really, bidirectional search can really benefit us. So far, we have been discussing the case of uninformed bias, where the agent has minimal information. It only knows at any given time what state it is and what the direction or the action it can take in that state, what are the cost of each of the actions, and as the result of the action which states is reach, right? But if you have more information, and which can happen in many applications, then you can perhaps do better. So one of the possibilities that we discuss is that when the agent is at any given state or node in the graph, it has some estimate of the node, of the cost from the node to the goal. And in fact, if you are at a state and there are many possibilities to go taking action to other states, and for all those states, it has some estimate of the cost from those nodes to the goal, then we can do perhaps better than the previous algorithms. In this case, greedy best first strategy is to choose Fn to be equal to Hn. Hn is at node n, the estimated cost to go from n to the goal state. We are saying estimate, it's a guess. It may not be the exact cost, because if it is the exact cost, then you can just take the node, go to the node which has the minimum cost to go to the destination. However, often that information may not be available, and we may just have some estimates, which may or may not be very accurate. This algorithm, so what you are going to do it, you are at any node n, and you have to go to the next nodes, pick the node with the minimum Hn, and you choose the action. This algorithm is complete in finite spaces, but not in infinite spaces, for some of the reasons that we have discussed earlier. Its worst case time and space complexities of the order of mod v, where mod v is the number of vertices or nodes in the graph. If you have a good heuristic, good estimate of cost from the current node and node n to the goal, then we can do better and reduce the complexity to of the order of d into m. Example, we take the same example they have been taking. Suppose, so A is the root node and G or H is the goal. Suppose, so from initially you are starting at A, and we have to either pick B or C. These are the only possibilities at that time. And if you have an estimate that from B to the goal which is G or H is 8, the estimate from C is 7, then from A, because Fn is equal to Hn, from A we are going to choose the node C. So we know, as we know, this will not provide the optimal path. Therefore, it shows if the guesses on Hn are not very good, it may give you a solution which may not be a least cost path. So even for a finite state space, finite number of nodes in the graph, it will be complete. You are getting the solution, but it may not be least cost. A star algorithm, and this is a very well-known algorithm. It works in general pretty well. So in this case, what you will do is, again, for each node n, there is an estimate of cost from n to the goal node that we are calling Hn. So in this case, Fn for any n is going to be defined as Gn plus Hn, where Gn is the path cost from root node to the node n. So this is the path from root to node n. This is estimated guess from n to the goal node. So Fn is going to be the estimate of overall estimate of, if it go pass through n from A to the goal node. So if you are going to do the best first using this Fn, this is called A star algorithm, and this is a complete algorithm. In the sense, it will provide us optimum. It will provide a solution if there is a solution. Example, again, Hn we took Hb is equal to 8, Hc equal to 7, as we have taken earlier. Now, Gb is equal to 1. We know that Gb is equal to 1. And Gc, that is cost from A to C, is 3. So Fb is going to Gb plus Hb, 1 plus 8 equal to 9. Fc is 3, cost of Gc, plus 7, this is 10. So from A, you are going to go to the node which has minimum Fn, and that is node B. And you continue from there, repeating the algorithm. Suppose the estimate from B to the goal node is HB equal to 10. Now, in this case, but while HC is same as 9 given above, no, HC was taken at 7. So now the new FB is equal to 11, while FC was 10. So therefore, instead of going from A to B, within these other estimates of H, we'll go to A to C, and we know this will not give the optimal path. So this shows that if we have good estimates of H, which was the previous estimate, it helps to get the better routes. Now, here is a general result. If H is always underestimated, that means for each of the nodes, the estimate to the of cost to the destination node is less than or equal to the actual cost. So for example, if we take HB, the estimated cost to be 4 from B, but we see here that, of course, from estimated cost from B to G is 4. So that is satisfying the constraint that we are talking now. And if we take HC is equal to 3, so estimated cost to one of the goal nodes is 3. But if we are seeing here from C to H, this is one of the goal nodes, the cost is 4. And from C to G, it's going to be maybe path going this way. So this is about 8. And currently we are taking estimated SC to be 3. So therefore, this again underestimate and so on. So if you take H values for different nodes to be these quantities, these are underestimating H. If for all nodes we have chosen H which underestimate, then the A star algorithm obtained will give an optimal path. So this is a general result for A star algorithm, and the optimal path, of course, A, B, E, and G. And you can try taking these H's and use the algorithm. So as I said, A star is complete. If Hn never overestimates, then A star is cost optimal. It will provide the optimal solution. If Hn does overestimate, A star may not provide optimal solution. That also we have just seen in this example. A star is efficient from the time and energy case because it prunes away some of the search tree in the algorithm. If Hn, the estimates, are satisfying this constraint, Gn plus Hn, Gn is the cost from A to N, Hn is the cost from N, estimated cost from N to goal. If that quantity is less than equal to Gn plus N prime plus Cn N prime plus Hn prime, where C and N prime is any node which can be reached from node N in one step, so called successor node. And Cn prime is the cost of the link from N to N prime. If this inequality is satisfied for all nodes N and N prime, then H estimate is called consistent, and a general result is if. So earlier we have said if Hn never overestimates, A star is cost optimal. If H is consistent, then A star is optimally efficient. So it will be optimal and efficient algorithm. There is a variant of A star where Fn is taken as Fn is equal to Gn plus W into Hn, where W is greater than 1. If you take W is equal to 1, we'll get the A star algorithm. If take W greater than 1, this is weighted AR. So this has also been considered. Okay, although A star is very popular algorithm and it does pretty well, there are certain problems. One is it requires a lot of memory. Therefore, some improvements have been suggested to A star, which can reduce the memory usage. And those improvements we are not providing here. One can see in the literature. As we have discussed earlier, one can talk about bidirectional search for A star as well. So starting search from the root node as well as from the destination node. So these are the following results for the bidirectional case for A star. If we have a good estimate Hn for each n, then A star itself is good. Bidirectional does not help in this case. So you can just do with A star. If Hn is not necessarily very good, but not also very bad, very poor estimate for each n, then bidirectional A star can do better than A star. If Hn estimates are really poor, very rough estimates, then neither A star helps or bidirectional will help. Now the question is how to get good heuristic function Hn, because this is important in using A star. There are many methods in literature which have been suggested. We just mentioned them. One is by relaxing the problem definition. Next is defining some landmarks. In the graph that you have some landmarks. You can, some of the nodes you can identify as landmarks, which going to those nodes can help going towards the final destination. Then you can use distances or the costs for those landmarks as the in helping in finding Hn. You could, if the graph is large, you could consider parts of the graph at a time. So those will be smaller graphs. You can compute solutions in those cases and use those pre-computed solutions of the subgraph for the final main graph and try to get good heuristics that way. That is one possibility. The other is learning from experience. If you have worked on finding, from different routes to different destinations using the same graph you have used, that previously, or of similar graphs, that experience also you can use in designing good Hn functions, which, as we know, helps us. So we have provided here main algorithms in a basic setting of finding solutions for the agents. The setting was basic in the sense that you have the whole graph available and you know the edges, you know their weights, and everything is deterministically available to us. But in many realistic scenarios, there will be uncertainties in, let's say, weights. There can be uncertainties in which nodes are adjacent and so on. Now, in such cases, there are other methods available for search. One prominent one is reinforcement learning. This is one of the methods which is also used elsewhere in machine learning, and we are going to study that in the advanced course of module in this course. And there are, of course, many other things. We will search related things we'll be doing there. Thank you very much. And as I'm mentioning here, you want to learn more, you can go to our next advanced course.